Welcome, and thank you for joining today's OES-Environmental webinar series. Please note that all participant lines will be muted for the Q&A portion of the call. You're welcome to submit written questions throughout the presentation by selecting all panelists under the Send To drop-down menu of the chat panel located on the lower right-hand side of your screen. If you require technical assistance, send a note to the event producer. With that, I'll turn the call over to Andrea Copping. Please go ahead.
Thank you so much, Ronnie. Good afternoon or good morning. This is Andrea Copping with Pacific Northwest National Laboratories in the United States. I welcome you to this Ocean Energy Systems Environmental webinar. For many of you, you probably know this program as Annex 4. We're just in the process of changing that branding, so in future you'll be seeing OES-Environmental instead. We have a very exciting webinar today with a great lineup on biofouling on renewable energy devices. So with that, I want to turn it over to Andrew Want of Heriot-Watt University and EMAC. Please go ahead, Andrew.
Thank you, Andrea, and welcome everybody. Thank you for joining us today. We have a packed schedule today where we're talking about the issue of biofouling specifically towards the marine renewable energy sector, and we have representatives of test centers, of academic research, and of developers and manufacturers of coatings. I want to quickly explain the agenda for today. We have the following 5 speakers. I'll let you have a quick moment to read that over. There'll be a short introduction by Caitlin Long for EMAC, an overview of fouling by Joe Porter. I'll be talking about the BioFREE project. On the previous slide, I mentioned this, a major part of today's presentation will be on some of the results of the BioFREE project, which was funded through NERC. And then George Bonhayo will be discussing his work on coatings research. And lastly, we'll be having Gareth Berry, who represents Whitford, a coatings manufacturer. So without further ado, I'd like to pass on to our first speaker, which is Caitlin Long from EMAC.
Good afternoon, everyone. Well, it's afternoon here in the UK, and thank you very much for the introduction, Andrew. So I'm just going to talk about very briefly about the International Waters Network. So this network has facilitated the BioFREE project, and we hope will facilitate future research in other fields as well. So I thought it would be useful just to get an overview of that as a starter. So EMAC is the first and only centre of its kind to offer both tidal and wave developers purpose-built and accredited test facilities in real sea environments. However, there are many centres very similar to EMAC across the world, and EMAC foresaw the opportunity to collaborate across test centres and research centres globally and develop the International Waters Network. So here's just a sort of visual representation of some of the centres. This isn't all of them that are spread across the world, and it just shows how the global spread that there is. So we meet on an annual basis to share both our challenges and progress that we've made. This might be on a site development basis or on deployments that have happened. We also identify common test site opportunities that can support collaboration. We also review ongoing research and development within the sector, ensuring that any learning can be passed across to other test sites elsewhere. And we also look for areas of common ground where we can establish relationships and transfer knowledge. So why are we doing this? So we're seeking to make sure that this doesn't happen from the plug image there. This is crazy. So we want to make sure that there's a consistency in approach across the world, and this will allow comparison for commercial developments in the future. So these areas that I've listed to the side are areas that we focus on just now, but that will change as the sector matures. Ultimately, test centres are here to support industry, so through whatever means that we can. So to be honest, we are some of the first centres to overcome regulatory boundaries, so we can push that learning onto other test centres and other developers, commercial site developers. We're also some of the first to break down environmental challenges and to overcome those, so looking for research opportunities to overcome such challenges. So today that's one of the ones we're going to talk about is biofouling and that environmental challenge that is presented to developers. And lastly, I want to say that the International Waters Network should be seen as a knowledge transfer hub. Make sure that research can be transformed across international boundaries and can accelerate any research programs. So test centres to date have offered the main hub for deployments in the renewable energy industry. They can be used as an asset to stimulate and accelerate your research program. And I want you to take that home as the key message from this, from the International Waters Network. And I finally want to say, if anyone is interested from a test centre or research facility to join the International Waters Network, please come and let EMAC know. Our next meet is in October in Orkney, in sunny Orkney. And so if there's any research programmes out there that would like their research discussed and see whether or not that could be a collaboration opportunity, please submit it to EMAC and we can bring it to the table as well. So on that note, I'll pass across to Joe, who'll give you an overview of biofouling.
Good afternoon, everybody, and I'm going to just start talking first of all about what is the actual problem of today's topic. So we're talking about biofouling, and what we're really defining this as is the settlement and growth of organisms on submerged structures. We're talking about the impact that this kind of growth can have. So, for example, we can talk about increased roughness and weight, which can impact on drag, energy capture and functioning of devices. We're talking about accelerated corrosion of different components. Clearly, anti-fouling strategies are quite costly. These require additional operational downtime in order to apply any strategies. And also, an additional environmental consideration is that they could act as potential stepping stone habitats for spread of fouling communities, and this could include non-native species. So these are issues that we can't ignore and we need to try to address. We've got a couple of images here just on the right-hand side of the screen. So the top image is a mid-water mooring structure, which you can see is quite heavily fouled. And the lower image is an acoustic Doppler current profiler that was installed out at the Fall of Warness test site in Orkney and recovered after 20 months with quite a large amount of large barnacle fouling on it there. Probably saying to ourselves, well, is this a new problem? Our argument is yes, this is a new problem because there are several issues about biofouling that are unique to the marine renewable energy sector. Particularly, novel components are being used in this sector that haven't been used in previous sectors. Devices are also being placed in habitats which we've got very poor understanding of, especially when we're thinking about the very high tidal flow environments. It hasn't been usual for people to want to deploy devices in those type of areas before. In fact, they've been actively avoided, and therefore we've got very little actual background and basic knowledge about some of the fouling organisms that inhabit those areas. There's also things to consider in relation to sensor accuracy, because we're wanting to measure the actual resource of energy that's out there. And when the sensors become compromised due to biofouling, this can lead to an inaccurate determination of the device performance and the resource assessment. There's also some visual verifications required for certification at different locations with devices that have been deployed. And in particular, health and safety, when we try to access devices to do certification or to do inspections, biofouling can actually cause quite a considerable issue there. It's just allowing people to get onto devices to check things over. And a couple of other photos we've included here. The one on the left is a camera lens, which has become completely fouled and therefore no longer recording images. And on the right-hand side there, we can see that there's considerable biofouling on the inside of the cowling of a tidal turbine. So you never know where the fouling might turn up. So let's talk a little bit now about the sensitivity of the levelised cost of electricity in relation to capacity factor. And this is where we're talking about efficiency of machines. And if we look at the curve here, the higher the capacity factor, the better your return for your money. So if we're looking at a 1 megawatt device and say it's working at a capacity of 40%, then we have biofouling impacting, which might reduce this to 30%. What that means is that the levelised cost of electricity will be increased from £60 to £80. Now that is roughly a 30% increase in the levelised cost of the electricity. And as you move to the right of the curve, the differences in the levelised cost of electricity will be less. However, the margins of profitability for marine renewable energy are quite small, and so small changes in efficiency can make a difference. For some renewable energy devices, for example, tidal turbines, they're not running all the time at a high capacity factor. Therefore, at a lower capacity factor, the biofouling is likely to have a greater effect. And we started to do a bit of brainstorming within our team, thinking about a list of topics which might merit consideration when trying to analyse the risks that are posed by biofouling. And some of these topics on the slide will not be surprising. Some of these we've actually seen and have evidence of, and some of them we are inferring from issues from looking at the shipping situation. But a future challenge really is to understand how these particular risks, and probably some others that might not be on that slide, will relate to costs going forward. And as part of this overview, I just want to also highlight that there has been much work focused previously on the impact of fouling on ship hulls. And this includes the recent Globalist Partnerships project, which worked to build capacity to implement the Ballast Water Management Convention, which many of you, I'm sure, will have heard about. There's going to be a new Glofouling Partnerships project following on from the Globalist, looking to address the transfer of aquatic species through biofouling. And in this new project, there is, of course, an obvious focus on shipping, but other sectors may also be included, especially things like marine renewable energy. And this is particularly relevant to developing countries who will be planning to install devices for their own energy portfolios. So I'd like to finish there and pass over now to Dr. Andrew Want, who will present in more depth specifically about the BioFREE project.
Thank you, Joe, and thank you, Caitlin. As Joe's introduced, we now want to talk a little bit more detail about some fouling work which we have been conducting over the past year and a half or so. This is a collaboration between the Orkney campus at Heriot-Watt University and EMAC up in Orkney, funded largely through NERC. This is a very special partnership in that it gives the opportunity for scientists to work with operational teams and technical expertise throughout the sector. And I wanted to talk to you, go through these objectives here of what the project has planned and achieved. The first objective was to work in this understudied, data-poor, high-energy habitat, which Joe has already described, targeted by the industry. We don't know about fouling too well in this particular habitat, so we want to gather more data. Secondly, we wanted to develop a fit-for-purpose monitoring and testing system which would allow us to measure and test fouling and testing anti-fouling strategies in these habitats. That would allow us, again, as the third objective here, to test materials, use, and the strategies. I sort of repeated that one. And lastly, the other objective is to have outputs where we're providing guidance to help manage fouling. And this webinar would be included within that guidance. This is a means of helping to disseminate this information. EMAC, many of you are familiar with it and may have already visited the site. There are 4 main test areas. There is a full and a scale tidal site and a full and scale wave test sites. The first objective was to work with EMAC in their various operations to try to capture as much data as possible through various deployments, retrievals, and maintenance operations. So this slide is just sort of capturing several of the types of things we were doing, where it may be using panels, it might be doing surveys of Waverider buoys, and there's also experimentation which is occurring on panels, and this is in partnership with our colleagues at Whitford, which we'll discuss more later. During the BioFREE project, we've had a whole series of surveys that occurred opportunistically, and this table lists these, and I hope you can see with the resolution. The point is there is a large amount of data which can be collected. For example, in addition to the type of structure which is being surveyed, we can talk about its substrate, what it's made of, how deep it is, what the site is. And we're also identifying the dominant fouling organisms, the ones which are the major contribution, the main problems to that. And this slide just shows a few thumbnail photographs of some of the worst offenders, if you will. What we do with this data is we are doing some analysis with software called Primer. I should point out that we've identified in our studies in total just shy of 200 species that are found fouling on this infrastructure. And the Primer analysis allows us to cluster sites based on the assemblage of species in the various assemblages. And what we see from this particular diagram is there is quite a clear clustering on the lower right. These are sheltered marinas and such like. And the tidal sites are clustering on the left, and wave sites are clustering on the upper portion of that. So we're starting to have clearly identifying characteristic assemblages and dominant species which are based on the hydrodynamic conditions and the depth, allowing us to have increasingly more honing in on predictability of what type of species you would expect in certain areas. I'm going to go for a quick side point and show you another recent survey we did on a Waverider buoy. This particular one has only been deployed for 8 months, and in that period of time, a large amount of fouling occurred. We see on the right that the diameter is increased by about 7%. The weight of it outside of water is increased by about 9%. And this is largely because of the barnacle semi-balanists balanoides, which compromises most of this particular fouling. So pretty dramatic in a very short period of time, and it emphasizes the importance of seasonality in fouling. If this buoy was not deployed at that period of time, it would have been a different fouling species which may have dominated, and the consequences would have been quite different. So we're interested about what the implications are on this, on sensor behavior. And so previous research we've done, I want to highlight, we've looked at the heave response of these buoys and found that there is overall a very small change to the heave response, but that small change is identifiable in the high frequency spectra. And our idea here is that I should point out, much more data is necessary at this point, but you might be able to identify when a buoy has become sufficiently fouled. So it may help with the maintenance and the identification of when these problems are by looking at the spectral changes. And these same spectral changes might be occurring in surface devices as well. So not just devices, then there will be maybe a telltale sign of when fouling has occurred. So these opportunistic buoys, opportunistic surveys of things like buoys have allowed us to create like a diagram like this. And we've led to some important observations of the type of fouling we get at different depths and on different materials. But it's also made us be aware of the limitations of these opportunistic surveys. Typically, it might be fairly straightforward and not too hard to get a survey of a surface device. It might be too hard to get moorings. But what about in the middle? If you imagine a tidal turbine and its behavior in the middle of the water column, we don't have that much data. How can we grab this data? Well, our second big objective was to develop a monitoring system which would allow us to capture data at any depth, at any deployment location. A system which would allow testing of different materials and different anti-fouling coatings, and it would allow easy deployment, easy retrieval for regular access, and we wanted to design a system which would be physically robust to survive these very high current devices and high wave conditions, and also statistically robust to give some scientific rigor to these studies. So we have worked in consultation with hydrodynamicists and statisticians, and we've worked to manufacture these frames, which have been supported with help from Whitford Limited. These frames have been sent out to international partners who are participating in the BioFREE program. Here's a list of them. So we have PNNL, Oregon State University. We have a research group in Nagasaki, Japan, Professor Chuzuko. And we have Sergio Navarrete in Las Cruces, Chile, who are all participating in this project. To show you a very simple schematic of the system, the frame is deployed at any depth in the water column. It consists of an array of 12 panels which are made of different materials. Upon consultation in the industry, we've equipped it with HDPE, high density polyethylene, and steel and coated steel panels. And those have been assigned in a randomized block design. So, what has come back? Well, the first thing to say is that we're very happy we've had total success so far. We've had retrieval of all these devices. These were deployed in July. These are representatives. They're in duplicate. These are one from each of the 4 sites. So we are measuring the encrusting sessile species as well as any mobile invertebrates which might be in the turf or on the structures. We're seeing that in the first 3 of these, so forgetting the bottom right for a second, that the main dominants at this point are hydroids, which is not surprisingly these are early successional organisms, but it's also to do with the seasonality. This is happening at the very end of the summer here and into the autumn, so these are autumnal fouling going on here. And these are also typical of high-flow habitats. We'll notice again that in the bottom right on scapa flow, there isn't really hydroids very much. Instead, there's more of the calcareous tube worms, and that is possibly due to that being not a high-flow habitat. You'll notice, maybe you can't tell from the images, but I can tell you that there are no barnacles at all, which of course are a major fouling organism. This is unsurprising, again, simply because of the seasonality. These were deployed at a time before the barnacles had settled. This is preliminary data. I'm going to talk to you in a little bit more detail, but I want to say we're continuing this collection, and I'm very, very happy to say that as we speak right now, literally as we speak, the EMAC operations team are in fact gathering this next quarterly data. So the winter data is being recorded, or being collected, I should say, as we speak. So my weekend is going to be very full looking over the panels. So a few sort of some stats to show you. Again, this is very, very preliminary at this point. We have deployments occurring in 4 different sites, the 4 different wave and tidal sites, and we've identified the dominant fouling organisms in those different sites. Looking at the graph on the bottom left, we're seeing a difference in the amount of fouling that's found on HTP versus coated steel. Unsurprising because it has coatings on it, but possibly there might also be a preference for HTP as a substrate. And on the bottom right, we're having a comparison of fouling between HTP and coated steel between the 4 sites. And what we're finding here is that the greatest amount of fouling is occurring. Again, this is only indicative data because it's quite early on in the studies, but the fouling is correlated with the tidal speed. So the highest tidal speed has the highest amount of fouling, and in fact it goes proportionally down based upon the current speeds. We're also seeing that the greatest difference between HTP and coated is in that highest tidal site, so suggesting that the coated panels may be offering some protection from fouling in higher tidal velocities. These panels are taken out quarterly. They're retrieved quarterly, images are taken, and some of the panels are retrieved, and fresh panels are put in. That way there are always fresh panels to allow the latest organisms seasonally to have an opportunity to settle, and this is part of our seasonality and successional studies. So the image on the upper left shows one that's just been retrieved and fresh panels have been added just before it becomes redeployed again. I also wanted to show this image on the right. This is from Nagasaki. I don't have any data, detail to present to you today, but with our colleagues in Nagasaki, we see that over the similar sort of time period, much heavier fouling in these waters and entirely different species. And of course, this is not surprising by any means, but if you are a developer in this industry, it may be very vital for this information to be shared. So I want to begin wrapping things up with a review of the main findings that we have so far come upon. Now, when I say findings, this also is not only necessarily new information, but also confirmation of information that is already known. So I'm just going to talk you through this list real briefly. We found that the monitoring and testing system is proven successful. It has survived in these very difficult conditions, so we're very, very happy about that. We have found that fouling is highly specific based on location and also based on substrate, and it varies based on substrate type, and that these assemblages are highly predictable based on hydrodynamic conditions and deployment depth. Use that buoy, as I mentioned in the example earlier, you can get profound amounts of fouling occurring in a very short period of time. And to go back to a question raised earlier by Joe, as of today, we have no evidence of marine non-native species found at the high-energy test site in Orkney. It may in fact be that there is a hydrographic barrier that's created by these extreme forces. A few more findings of the fouling research. Anti-fouling coatings. So far, this preliminary data have been most effective in high current flow conditions. I haven't spoken about it much in today's talk, but orientation of the substrate appears to be very, very important in when things settle and how they settle, and so that may help us understand better the hydrodynamics of how settlement and growth occurs. We spoke a little bit about sensor functioning, how this is compromised by fouling, and how that we may use that as a tool to identify fouling, and that there is a marked seasonality of fouling. I guess one of the main points of this, and from the industry standpoint, is that by scheduling, by this knowledge of knowing when fouling occurs at a specific location, geographically speaking, depth speaking, to do with the hydrodynamic conditions, we might be able to schedule deployment, schedule maintenance operations in a targeted manner so that you best manage the issue of fouling and can remove fouling most effectively or prevent fouling from occurring most effectively. I've got a little traffic light system table here identifying the major periods of time in our waters up in the North Atlantic of when the major foulers are problematic. A lot of them are in the summertime, a lot of them in the springtime, but they're not all that time. And so this is all valuable information to know. And I want to leave with just an example of what sort of cost this might have. This is hypothetical, but based upon discussions with developers. Conservative estimates suggest that if you would, the cost of visiting one of these large structures, for example, to retrieve a large turbine out of the water, from the boat hire and the cost of fuel, etc., may be costing £20,000 and using 4 tons of carbon. If you were to scale that up to an array of 10 devices over 25 years, it translates to £5 million of savings and 1 kiloton of carbon savings. And lastly, as Joe was mentioning with the LCOE graph that she presented, if you had, for example, a 3% improvement in energy capture, this is a very broad statement I'm making, through properly managed fouling of one of these devices that's currently in the Penland Firth, an estimated savings annually of 41 tons of carbon, as well as obviously improvement in the energy capture and the cost lowering. So with that, I would like to send a big thanks to the many, many, many people which this work would not have been possible without. And I would also like to offer to people that here's my contact number. If you have any questions about this program, please get in contact. And to the attendees right now, just remind you that feel free to come with any questions for Caitlin earlier, Joe after that, myself, and the next 2 speakers. Feel free to ask any questions, and we'll try to answer those as we can. So that's it from me for now. I'm now going to pass on to George Bonhayo at PNNL. Take it away, George.
Thank you, Andrew. Okay, so today I'm going to talk a little bit about some of the coatings research and a focus on microfouling that we're doing at the Pacific Northwest National Laboratory. If I can get the slides to advance. Do I have control of the slides?
George, you currently have presenting rights. If you go ahead and click on the presentation first and then use either the space bar or the page up and page down buttons on your keyboard to advance.
Oh, there it goes. Apologize for that. Yeah, so I'm located at the Pacific Northwest National Laboratory in the state of Washington. PNNL is one of the U.S. Department of Energy national laboratories. The work that I'll be talking about today is primarily happening at our Marine Research Laboratory, which is in Sequim, Washington, up on the Olympic Peninsula. There's an aerial photo down in the bottom of the picture there. I should note that I also have a joint appointment with Washington State University. For those not familiar with it, PNNL, as one of the large Department of Energy laboratories, has about 4,500 staff. PNNL has DOE's only Marine Science Laboratory. That laboratory, again in Sequim, has about 44 on-site staff. highly characterized bay and tidal channel, and some pre-permitted seafloor locations where we do our fouling and marine research. So what I want to talk about today is a little bit about what the big challenges. We had a terrific introduction from Joe Porter about biofouling and some of its effects. I'll talk about the focus of one of the Department of Energy programs called the Advanced Materials Program, some of the work that we've been doing on developing standardized methods, particularly quantitative methods that help us do comparisons of composite materials and coatings, and then a little discussion of some of the new coatings research that's going on. So again, Joe did a great job introducing the fouling process. Different sort of perspective here. Oftentimes we look at fouling as being a four-stage process, beginning with a conditioning film, which is a collection of biomolecules on a surface, followed by the accumulation of unicellular organisms that develop a biofilm. That biofilm assists in the recruitment of large macroorganisms. The reason I wanted to put this slide in here is the consequence of those first two stages often is that the microorganisms and the biofilm accumulation can alter the surface properties of a coating, a composite, or an alloy that goes in the surface. So even at those early stages, despite an anti-fouling coating, we can change, the microorganisms will change the properties, leading to downstream consequences. Traditionally, the way of fighting fouling has been toxic paints. The marine renewable energy community has focused on trying to go towards non-toxic paints in keeping with the green energy focus, lower environmental impact. So I'll be talking quite a bit about a newer class of anti-fouling paints known as foul release coatings that don't use toxins. So the Advanced Materials Program, this again is a program funded through the U.S. Department of Energy. The quick summary is that we are looking to address the barriers, some of the uncertainty that exists in using composite materials for marine and hydrokinetic or marine renewable energy systems. So composite materials offer the promise of high strength to low weight ratios. They've been extremely beneficial to the wind industry, and the hope is that some of those benefits could translate well into the marine environment, with a potential additional benefit of very low corrosion relative to metallic alloys. Through the program, one of the things that we are working on is taking the data that we generate about the performance of different composites, the performance of the coatings, and then putting that out there as a resource for the industry to use, the marine renewables industry to use, to help select composite materials, to help select coatings, to put on their structures down to the level of detail of knowing which composite or whether an alloy should be used for different substructural elements. Things that we are looking at include the prevention of fouling, examining corrosion, particularly where we have dissimilar materials, composite on composite, metal alloy on composite. Carbon fiber tends to be one of the particular challenges if it's joined with a metal because of galvanic corrosion. And then looking at how the composites perform through time, whether there's the potential for deformation of the composite material, weakening due to water absorption, so quite a lot of load studies that are going on. Just a quick introduction to the team for this program. Sandia National Laboratory, Bernie Hernandez-Sanchez is the lead for the program there. Also at Sandia, we have Budi Gunawan, who's working on sensor systems that can be embedded into the composite materials, into the substructures for monitoring. Myself at PNNL with a rather large team. Scott Hughes at the Department of Energy's National Renewable Energy Laboratory is helping us with substructure testing. Montana State University, David Miller with some of the composite performance and fabrication. and Francisco Moreno at Florida Atlantic University is leading the galvanic potential studies. So this program began in 2017 and is continuing through this year. Early in 2017, we began with some of the fouling studies. We wanted to get samples into the water as quickly as possible to allow for about a 2.5-year exposure period. In 2018, we began some of the composite and metal galvanic corrosion studies, also began looking at some subscale elements and joined materials for strength testing. That's the picture down in the center there. I should note that samples were either fabricated by Montana State University, Sandia, and NREL, or they were provided by industry, and there's a list there in that green box. And now in 2019, or fiscal year 2019, we are beginning some tests with full-scale subcomponents, as well as some additional studies with some new composites and the dissimilar joined materials. So the composites themselves, without reading through the list, here is a list of some of the materials that we are looking at. In terms of the joined materials, primarily focusing on, again, carbon fiber, joined out of 316L stainless, Monel, titanium fixtures, and then it looks like we may be adding some duplex or Hastelloy C as an additional metal. So I want to talk a little bit about measurement. So one of the big challenges that the community, the anti-fouling, biofouling community has seen is how to actually quantitatively measure fouling. American Standards, ASTM group, has methods out there that are purely observational, drawing an imaginary grid on a coupon and then counting the number of barnacles, tunicates, and a large number of other species. As Andrew pointed out in his talk, there are innumerable species that can be observed on coupons. Those vary from season to season, location to location. Simply doing a hand count doesn't give a real quantitative measure of exactly how much fouling has accumulated on a surface. And if we need to compare coatings, need to compare the performance of materials, we need to be able to put hard numbers on those in order to understand when we're making an improvement in the coating, an improvement in the deployment. The other challenge is, again, you got an impression of this from Andrew's talk, and you can see in some of my pictures, we have very large numbers of samples that we get. We need to look at many different coatings, sometimes coatings applied in different manners onto different substrates, coatings that go in at different time points during the year, come out at different time points in the year. So any methodology that's developed has to be simple, cost-effective, and high throughput, and again, leading to highly reproducible, highly quantitative data. And again, doing these observational methods doesn't lend itself very well to that. You need expertise in understanding the organisms. You would need to have a small army of marine biologists to look at the coupons and do those sort of hand counts. So what we have done and what we're doing, working with folks like Andrew and EMAC, is trying to develop some standardized methods, both for the exposures. A critical feature for the marine and hydrokinetic industry is the relative flow rate across the surface. The anti-fouling coating industry has really been dominated by the shipping industry for many years now, and ships move at high velocities. They don't make money if they're not delivering their product from one country across the ocean to another in a short period of time. But in wave energy and tidal energy settings, we're typically looking at velocities that may be as low as 2.5 meters per second, sometimes even lower. Off the coast of Orkney Island, they're fortunate in that they have some of the highest tidal velocities that there are, but here in the United States, for example, off of Oregon and in the Straits of Juan de Fuca, 5 knots, 2.5 meters per second is about our peak velocity. So when we do our exposures, we look at low flow conditions in controlled tanks, either using relatively static tanks and then a large tank system where we have variable speed control. We do studies in natural environments. Squim Bay, we do have a channel where we have tidal velocities approaching 2 meters per second. And then we can also do some controlled studies in tanks with very specific organisms, mussels, barnacles, microorganisms, if we need to look for a particular effect. So some of the quantitative methods. For looking at microfouling, one of the things that we developed at PNNL is a photographic and visual-based method where we take a coupon, apply a set of stains. Those stains help reveal the organisms, but they introduce colors such that when we take a digital photograph, we can separate the color channels, and then with a software script that we've written, measure pixel by pixel exactly how much fouling has accumulated on the surface. We've also developed a method for doing total organic and total nitrogen quantitation, so we can take a coupon. With an extraction procedure we've developed, we can remove both the soft fouling and hard fouling off of that surface without damaging the coating, and then process a number of samples through a standard laboratory TON apparatus to get a hard number of the total accumulation of organic matter that's there. We're now adapting that such that we can also measure the amount of hard-shelled organisms that are present. Additional methods that we use, wet and dry mass measurements. We have found that by using a simple hand dryer, it's a little bit silly, but it knocks off all of the unbound water, so we get very reproducible measurements of wet fouling. And then by drying the coupons, we can get the hard-shelled organisms that accumulate. So it provides an ability to differentiate between how much mass is provided by soft organisms such as tunicates and sea anemones versus hard-shelled organisms like mussels and barnacles. We do a lot of contact angle measurements. This allows us to look at the surface energy of a coating, particularly for those foul release coatings and some hydrophobic coatings. So this is a measure of how attractive a surface is to water or to an oil. And we can measure those changes through time as fouling occurs. And then adhesive force measurements, the ability to look at how strongly a mussel or a barnacle sticks to a surface. So a little bit right now on foul release coatings. So again, traditionally, anti-fouling was achieved through the application of toxins, copper being one of the most popular. Tributyl tin had been widely used in the world until about 2005, 2008. That was found to be too damaging to the marine environment. There is a movement now in many nations to abandon the use of copper. New focus is on so-called foul release coatings. These are coatings that have low surface energy, low adhesive capability for organisms to attach so that the currents that are available in the environment can help knock the organism off, or at the very least during an operations and maintenance cycle, it's easy to wash away the organisms and then put your device back into the environment. At our laboratory, again through DOE funding, we are looking at a coating that's inspired by nature, features of the pitcher plant, lotus leaf, and fish slime. It's a non-toxic, actually self-healing coating. It involves, if you look at that bluish image in the middle there, it involves applying a structural feature to the surface of the device, infusing a oil or grease into that, and we are working with a company that makes oils based on canola oil, so a natural plant-based oil. This coating provides both then a hard porous structure that itself has some anti-fouling properties, and then this grease that acts sort of like a fish slime to keep organisms from settling. Previously, through DOE, we had done some studies looking at fouling release coatings modified with additional features such as saragenins, which are synthetic peptides, or the addition of copper and silver to prevent fouling. This work is currently underway. We have some very good data from using this material for other purposes, such as biomedical devices. We will have data generated on that around this time next year, or actually December. Some real quick notes on the fouling studies to date. We have our second set of coupons. These were 14-month exposures coming out of the water now. We will be finishing up the composite study for the fouling aspect in the August-September timeframe and putting all of the data and the reports onto that Sandia website that I showed earlier, and I believe that will be shown in the slides, which will be made available on the TEFAS website. So that, just want to wrap up. Note a large number of collaborators that are on here, and introduce our next speaker, who is Gareth Berry at Whitford, who's going to be talking about the industrial perspective on anti-fouling and anti-corrosion.
Thank you, George, and good afternoon to all of the attendees. I have the pleasure of finishing the presentations today. We are running a little bit behind time, so I will try and move it forward accordingly. So just let me see if I have control of this. Just bear with me a second, please. There we go. Thank you. So my name is Gareth Berry. I work for Whitford, which is currently a privately owned American corporation, but more of that later. I have the responsibility for looking after our energy markets, whether they be black, blue or green, and I'm based out of our UK operation in Runcorn between Liverpool and Manchester, for those of you that know the geography of the northwest of England. Moving on. I think I put a strap line on the bottom there from an industry standpoint, a coatings industry standpoint, is we have to be realistic. We have to accept that we will never remove the risk of either corrosion in whatever format that is, whether that be red rust or galvanic, or fouling. We will never remove fully that happening in these marine environments. And particularly, some of the other presenters have said, in the renewable energy environment where we're dealing with wave and tidal structures, these are in areas that we really have never investigated fully or fully understand how the fouling manifests itself when and where. So I think in summary there, we can inhibit both of those elements of corrosion and fouling, but not totally prevent it from happening. And I think we have to be realistic with that particular message. If we look at the approach we've used in Whitford, we have been involved in coatings for many years, some 40 years now. And our coatings are very specific, and they are very thin. They are not the type of paint you would find on static structures in a marine environment. They are 50 microns, which is not much less than the average width of a human hair. we started our approach with incorporating fouling inhibition in amongst everything else which the coatings deliver in one package. So these would be such things as corrosion resistance, abrasion resistance, chemical resistance, to name just a few. And it was how we put the anti-fouling technology into those existing packages rather than develop a new solely fouling inhibition coating. That wasn't our aim. So we were very pleased to come on to the program at the behest of the other participants. In terms of what we see the industry needs, following some feedback, ultimately the coating has got to be able to adhere to multiple metallogies. I think, as George mentioned earlier, they are looking at duplexes, carbon steels, and many other metallogies as well. But the coating must be able to adhere to many metallogies, as there are mixed metallogies and lots of metallogies used in this particular sensor. They have to be operating in a wide in-service temperature environment. So incorporating our current temperature ranges, which are at plus 260 right down to the minuses, so minus 150 in some cases. So we already have that built into our systems, and we wanted to maintain that. They've got to be application friendly, so the person who is, or the organisation that is actually applying these coatings has got to have a relative ease at which they can apply it. It's no use having something which is difficult to apply, because ultimately it's got to be a commercially viable process. And they've got to be able to cure on a broad temperature range. So in terms of our coatings, they are heat cured, they are baked on, and some of these cure temperatures can range up to 220 degrees, and we have to make sure that we can have lower cure temperatures as well in order not to affect the properties of some of the metallogies where they're annealed, etc. And it would be very nice to have several colours as well, so you can actually see them when they're in darker environments or subsea environments. But ultimately, and probably the most important thing that I try to talk to people around, is the fact that we are not in the game of developing a new coating for whole structures. We are trying to incorporate the anti-fouling technology into our current range of coatings to protect strategic components. And this could be some of the images, components in the images that you've seen earlier. For instance, Joe showed one of the internal of a blade, I believe, and on that blade there were some fasteners, and it's no use having the fasteners free from corrosion but full of fouling, which means you can't break the fastener from the hub connection, the blade from the hub connection. That sort of defeats the object. So this is where our approach was directed. Andrea showed you some of the images from the plates which we submitted. Alongside that, we've also had ongoing development and testing with our aim of incorporating the fouling technologies in our current coatings for some time. And here you can see an image of one of our test panels, which is located in the intertidal zone in Stromness. And circled on the left-hand side, you can see one of our more common coatings, is Xylan 1424, which has simply is a corrosion inhibitor. There is no fouling inhibition properties within that particular coating formulation there. Exactly the same coating we've taken and added some fouling inhibition properties into it using various chemistries and ingredients. And in this particular case, you can see that both the panels highlighted on the left and the panels highlighted on the right have been exposed to the same environment for a period of 18 months. And if you were to look at the panels on the right, you can see there is very little settlement. So clearly we're doing something right with the progress that we are making. if I refer you back to that previous panel, that previous holder, you can see
And Gareth, your line is still connected, but we're not getting any audio coming from you. And once again, Gareth, your line is connected, but we're not getting any audio coming from you. And Gareth's line seems to have dropped off at the moment.
Ronnie, can you hear me?
Yes, you're coming in loud and clear.
Should I take over now? Is that probably the best thing to do with this option?
You may have to. Gareth's line's dropped off. I've been sending messages over the chat panel.
Off, yeah. Well, that's just the slide. Hello, everybody. This is Andrew once again. We appear to be having some technical issues with Gareth Berry, and I don't think he knows actually that we're not getting audio. I think he's continuing with his presentation. So apologies for that. I think at this moment we're going to turn to some of the questions which are coming through, so thanks for the questions. We have a question from Antoine Bonnell, and the question is about hydrophobic coatings. Question is it only applicable for paints and composites, or could it also be put directly on metal surfaces like dynamic sealing surfaces? I'm wondering whether or not, George von Hayo, if you might be able to address that question.
Oh, hi, Andrew, can you hear me?
I can, George, yep.
Okay, yes. So many of the hydrophobic coatings can be applied to a variety of surfaces. In some cases, you may need to have a primer. The hydrophobic coatings in and of themselves, we have found don't tend to work very well, at least not based on hydrophobicity. With a lot of those depend on there being an air layer of air that's captured on the coating. They're typically a microsilica type of structure, and with time that air layer can be dissolved into the surrounding water, or with depth and abrasion, either the pressure can introduce water into that layer, or the, again, abrasion by sand and whatnot can damage it. The foul release coatings have a slightly different technology than just hydrophobicity that allows them to work well, so that's often what we recommend.
Thank you, George. Excellent presentation, by the way, George, earlier. We have another question I'd like to address, which is from, if I'm pronouncing it correctly, Iwell Roberts. Has a question about fouling in Taiwanese waters and about whether or not we have any detailed information on in Taiwanese waters and specifically in the shallow water. Can anybody point us in the direction of a data set or organization that might help? Well, I can say that we are certainly working on trying to gather a greater data set from international waters. Officially, I can make comments about the shallow water is in the aphotic zone, in the photic zone, and we'd expect there to be macroalgae and microalgae, for that matter, fouling in there as well. But as far as actual data sets itself, Caitlin has...
Yes, so there's a test center for renewable energy in Taiwan called TAMETS. It's only recently established. So I can put you in contact with the correct university. I think actually I've got your email address, Howell, so I'll give you the right person to contact in that case. That's great, Caitlin. So yes, so Caitlin, so Howell, you have Caitlin's details. Also, you'll have my details as well. So if you have any questions specifically, I can look into trying to source that information for you as well. Okay. Gareth apparently is back again now. So if I could ask our administrator, Ronnie, if you could help Gareth out with continuation of his presentation. And can I also ask people to continue firing out those questions?
And Gareth, you have presenting rights again.
Thank you very much, everyone. My apologies for that. It must be the lines here in Norway that have caused the problem. So I'm hoping you heard me up until this particular slide. And what I was indicating before I was so rudely cut off was that the takeaways which we as Whitford have taken away from our involvement in the BioFREE programme. Clearly, it's an absolute must that we must have a multi-stakeholder approach as well as a multinational approach, because without this, we will not begin to solve some of the issues which are caused by fouling, particularly in the world of wave and tidal energy generation. We've established, which I think was already known, but we've confirmed that the levels of corrosion and fouling inhibition really are significantly affected by several factors, some of which are physical location of the component which is being protected, its water depth, and the oxygenation of that water at that particular level. The water temperature has an impact, as well as the levels of salinity which we are seeing in that localized environment. All of these have an effect on the level of corrosion and fouling inhibition. And it's also reconfirmed our belief that, for the sake of the people that are using or looking for anti-fouling, typically you're going to be applying it on metals, and therefore they don't just want anti-fouling properties within the solution. They want to be able to deal with some of the other issues which they see in these marine environments, in particular corrosion. So having a multifaceted solution which deals with corrosion issues and fouling issues, we believe is very much the right direction of travel for us. Just a brief bit about ourselves as Whitford. We've been around for a number of years now, as you can see, since 1969. We currently have around 750 plus. It's always a plus, could be 751 or 2 colleagues working worldwide, speaking many languages and dialects. In terms of our production sites, we have 11 dotted globally, North America, South America, Asia, and Europe. We put a lot of effort back into our R&D, with typically 8% of global revenue going back solely into our R&D capabilities and actions, and we have 8 fully staffed R&D laboratories worldwide. However, literally today, and I believe it's within hours, Whitford will become part of the PPG organisation, so we will be no longer privately held as a small American corporation. We have been purchased by PPG, and Whitford will come within that family, and the Xylem range of products will now come under the PPG banners moving forward. So that is literally happening within hours, potentially 1 or 2 days from the discussions today. So finally, you can find out more concerning Whitford, our actions, and indeed you can see some of the details from our test sites that we have, in particular at EMAC in Orkney, where we are testing many coatings, on our social media platforms, of which you can see some here. And when you receive the presentations, you'll be able to click through, particularly to our private YouTube channel. Thank you very much. Let me hand control back to Andrew as Master of Ceremonies, and let's take it from there.
Great. Thank you very much, Gareth. Excellent presentation, and again, sorry about the dropping out there for a period of time. We have a couple more questions here to address. So we have a question from Colin Anderson, who's a question about the specific types of coatings that are being used, and about the existing coatings that are found in leisure craft and existing ones that are applied for static and low tidal waters. Question is, won't these same ones work for marine energy devices? I'll start a little bit to answer that question, but I hope Gareth will be able to, from his expertise in coatings, will be able to continue this. But one of the issues with the environments that we're working in here is that they're unique in the hydrodynamic forces of them, and also the structures that are being placed in the water are far more complex, and they have a lot of they may have materials which haven't previously been tested. So sometimes, for example, couplings between devices where there might be a communication of one part with another part, they may be using materials which have not previously been used, and they may not be appropriate for those type of coatings that do exist. There are also what you get a lot of what you call niche environments, where you get small little areas that you also do, I should point out, you do get them on ships as well. You do get areas where they are prone for fouling. It's difficult to get rid of them. But there are unique issues associated with these devices. And the last point I wanted to make, which is very important, especially in high tidal environments, what may be the big issue in some cases may in fact not be fouling so much, but it may be damage to anti-corrosive coatings that's caused by scour and other forces as sediment is washed through the area, and that may be damaging the coatings. But I don't know if, Gareth, if you're able to add any other additional thoughts on how coatings may differ between those two environments?
Yes, let me try and throw some light on that one. In terms of the technology which we employ within our coatings, if you recall from my presentation, I said we were trying to build in the fouling inhibition into current coatings which are heavily specified in the marketplace or in a marine environment. The current range of coatings which we're adding the inhibition to are generally fluoropolymer based. They are as I say, very thin coatings, but they are relatively inert. So once they're cured, typically what you'd expect to see from VOCs, volatile organic compounds, have already been removed during the coating curing process. So they will be quite inert. They have been used in the marine environment for many years. So we take it pretty much that they have no specific effect per se in those surrounding areas. The addition of the fouling additives into them are environmentally friendly, and I think George indicated that there's a move away from the likes of coppers, etc., being used on these type of coatings. I think the one thing we have to bear in mind with the development work we're undertaking and our principal aim to make a multifunctional coating is that we are trying not to affect the other aspects of the coating in terms of its corrosion inhibition in particular by the addition of fouling inhibition additives into it. And it's quite a fine line to tread, but by making it so efficient in one area, you begin to affect its efficiency or performance in another area. So hopefully that answers some of the queries there.
Thank you, Gareth. Yes, so that hopefully answers the questions from Colin and from Sylvan. Colin and Sylvan, again, get in contact if you need some further details on that. I think at this point we are going to wrap up the webinar, and I want to extend a great thanks to everybody for attending and listening today, and to all the speakers. And I just wanted to end by passing over to Andrea, who's going to make a couple of closing statements.
Yeah, thanks so much, Andrew. Thanks to all the speakers. That was a great webinar. Could someone just move the slide forward, please? I just wanted to let you know that this webinar has been recorded, and it will be made available on the TEFAS website. If you don't know TEFAS, please get over there and take a look, tefas.pnnl.gov, and that's the link, but you can just go on to TEFAS and search under webinars. Also, please watch for announcements on TEFAS for upcoming webinars in future. And if you're not on our webinar mailing list, there's a link to join, and we'll let you know of any of those. And that's about it. Again, many thanks to the speakers. I think this was a great set of presentations. And with that, I think we'll conclude this presentation.
That concludes our conference. Thank you for using AT&T Event Conferencing Enhanced. You may now disconnect.